Today we showcase the zero-touch energy-saving xApp running on the RIC-TaaP by intelligently reassigning users and deactivating underutilized cells. The xApp reduces energy consumption while preserving quality of service KPIs. The xApp continuously monitors cell load using physical resource block utilization. Underutilized cells are identified, users are reassigned to suitable neighboring cells, and once traffic is cleared, the cell is deactivated to save energy without impacting service quality. This use case is demonstrated in a 5G NR scenario based on NS3 with 5G node and 15 UEs operating under realistic radio conditions. The challenge is converting algorithm-level decisions into standardized O-RAN E2 signaling, while keeping control payloads efficient and compliant. Let's now walk through the demo step by step. We begin by starting the near real-time RIC. FlexRIC is up and running, exposing its service models and ready to accept connections from both the simulator and the xApps. Next, on the RIC-TaaP Studio, we enable the connection flag to link FlexRIC with the NS-O-RAN simulator, or we can simply select a predefined scenario. We then configure the scenario parameters. Here we set the number of UEs, the inter-site distance, the number of G-node Bs, and the relevant scenario flags. Controls to start, stop, and reset the simulation are available at any time. Now we launch the simulator. The network initializes with 5 G-node Bs and 15 UEs distributed across the map. On the screen we can clearly observe per cell energy consumption, UE to cell associations, real-time UE positions. This gives us full visibility into both radio behavior and energy usage. Next, we start the energy-saving xApp that as soon as it starts, the xApp begins monitoring network conditions and reporting measurements through the RIC. The xApp confirms that the PRB history window is active and starts tracking PRB utilization trends for each cell to detect underutilization. At this point, cell 2 is meeting the PRB usage condition. The xApp continues sampling to confirm that this is a stable condition. PRB usage is evaluated at sample 3, and again at sample 4. Meanwhile, the simulator continues generating realistic radio conditions using the 3GPP UMI Street Canyon model, operating at band N78 with 20 MHz bandwidth. Each UE transmits 1.6 megabits per second of UDP traffic. At sample 5, cell 2 still meets the action condition. Its PRB usage remains consistently below 40%. Now the xApp moves to the mobility decision phase. It selects candidate neighboring cells for UEs connected to cell 2, based on SINR measurements and available capacity. For robustness, the xApp evaluates the SINR map over 5 samples to find out a target cell that meets the quality of service condition. This evaluation considers SINR measurement and frame error rates. We observe that UEs ID 13 and 15 are currently attached to cell 2. The xApp prepares the required mobility control actions. After completing the evaluation window, suitable neighboring cells are identified. The xApp generates RIC control messages using Connected Mobility Control Style 3 to trigger handover or conditional handover. The handover commands are sent. UEID 15 is handed over to cell 5. VID 13 is handed over to cell 3. The RIC successfully acknowledges these commands. In the GUI, we can immediately verify the results. UE 13 is now connected to cell 3. UE 15 is now connected to cell 5. With all UEs successfully migrated away from cell 2, the xApp initiates energy control. It sends a RIC control request to update the energy state of cell 2. Cell 2 is then deactivated, and its PRB usage drops to 0. Post-operation power consumption is displayed, showing an immediate and visible reduction in overall scenario energy usage, while preserving the quality of service required by the users. The final result shows an energy saving of 29.5% in this scenario. This demonstration highlights how a near real-time RIC and the energy saving under cell utilization xApp can reduce power consumption without compromising service quality by combining measurement-driven mobility management with selective cell deactivation.